Okay, let's start. This is a second class of advanced FEM. And normally what I like doing is just going through what we covered the last time. So I'm going to go very, very fast on this, but I want to do that just to bring everybody up to speed. So of course, in the first class, we looked at the elastostatics in one dimension. And well, we started by setting up the equilibrium equation. And then once we did that, we said, well, the boundary value problem is actually the partial differential equation. In this case, it's an ordinary differential equation plus the boundary conditions. And we talked about what are the types of boundary conditions that you can have for this problem. You can have essential boundary conditions, or the Dirichlet type. That's a mathematical term that is used on the primal field. So the displacement in this case is a primal field. In other problems like heat conduction, the primal field is going to be the temperature, right? But this is elasticity, so the primal field is displacements. You have natural boundary conditions, or Newman, on the dual field. So in this case, the tractions, or the axial force in this particular one-dimensional case, would be our natural boundary condition. And then you have mixed boundary conditions, which are, as the name implies, a combination of the previous two. And then we formulated, once we have the differential equation and the boundary conditions, we're ready to formulate the strong form of the boundary value problem. And we say, well, given some properties, and we talk about Young's modulus, the area, this constant that we described that can be used to denote some force that is opposing the movement of the bar, the load per unit length. Then find your displacement field U so that the differential equation is valid for every single point along the bar, right, with boundary conditions. And we talk about possible combinations. So we have two ends, and we can prescribe either kind of boundary condition at one end and either kind of boundary condition at the other end. And we talk about the possibility of having a pure Dirichlet problem where you basically enforce the displacement at both ends of the bar, or you can have a pure Newman problem, in which case you are enforcing or prescribing the axial force at the ends of the bar. But then there is a problem with this. Do you remember what was the problem when you have a pure Newman boundary value problem? So what we are not restricting here?
The rigid translation.
Correct. You're not restricting the rigid body motion, and therefore you can solve the problem up to a constant, right? So in other words, your system of equations eventually is a singular system, right? So what that means is that you have how many solutions? How many solutions you have to an infinite, to a singular system? I already said it. Okay. You have an infinite number of solutions, and of course, you can still solve for a singular system, but of course you pick one of those infinite solutions. Anyways, but we said that, what was the issue with the strong form? What was the main difficulty?
Many times it's not possible to solve it.
Many times it's not possible to solve it. In what times?
Well, in 2D, I find it easier. Because in many elasticity problems, when you have a really difficult geometry,
that is okay. Geometry. So, or boundary conditions, right? Uri, you're going to have to come here and start teaching. So, very good. So, the key thing here is that the moment you take this to a higher dimension, so in 1D everything is possible, is easy. The moment you take this to 2 dimensions and you have complicated geometry, or boundary conditions, then finding the exact solution, which basically means that your partial differential equation has to be valid for every point along that domain, and that at the same time you satisfy the boundary conditions, that is extremely hard to accomplish. And therefore we talked about the weak or variational form, which basically means, Uri, please.
Once you have one of the functions of the weight functions, you solve you find the solution that it will work on other, right?
Very good.
That domain.
Excellent. So that's what we do. What we say is, well, because I relax the restriction that the function u that I find has to be satisfying the differential equation everywhere, I relax that restriction. Point-wise, I don't need that, but I want that to be valid on average. And therefore, what we do is, well, we weight that differential equation with some function. We call that the test function or weight function, and we integrate over the domain right? In this case, 0 and L, that's a bar. And we say that that is going to be valid for every single W or weight function in some space. And we talk about spaces. We started talking about what is, in our case, the space we're interested in. And we define the energy space. And this is a very important space in finite element analysis because we use it all the time. Okay. In fact, yeah, one very important thing that we used, right, or something we normally do when we are trying to find new finite element formulations is to see how they behave. And you can see how they behave because if you have an exact solution, you can compute errors, and errors can be computed in L2 norm, right? You can compute an error on the quantity that you're using, but the energy norm is widely used because it's a norm, it's an error that considers the gradients. And you know that in finite element analysis, the derivatives are more accurate or less accurate than the displacement? Less accurate. So it is very important to see how our method is going to behave in the energy norm because the energy norm is actually considering gradients, and you can see that here, right? We have some gradient information right there. So we define this energy space, right, as the set, and I'm going to mathematically talk about this space, right? This energy space E that is valid on omega, which is our bar, our domain, is defined as the set, so these curly braces denote a set of functions V such that the energy, the strain energy, right, that is of course a function of that function V, and can be computed like this whole quantity is finite. That is what this expression is saying. It's less than infinite means it's finite. And this makes a lot of sense because, yeah, it doesn't really make sense for us to look at problems for which the strain energy is infinite, right? There are, by the way, there are lots of problems like that. There is a famous problem in civil engineering where you have basically a point load in an infinite subspace, right? That has an infinite strain energy. And that is something that actually you cannot solve easily with a finite element method because as you are refining the mesh, the application of the point load, right, keeps increasing the displacement, so the energy is infinite. But the moment you remove that first element, then you can compute a finite amount of energy. Anyways, that is, yeah.
What is the V in the energy space equation?
Sorry?
What is the V?
V is a function, any function. In fact, when we're computing a strain energy for a problem, we're going to use U, which is normally the symbol that we give to the primal field, okay? Okay, but now that we talked about the energy space, and of course we want to measure things. So how do we measure things? Well, we can create a norm, right? We define a norm, and essentially the norm is basically the square root of the strain energy. This is the way we define it. So similarly to when you have a Euclidean space and you define the norm of a vector, right? So that it denotes the length of that vector, right? It's the square root of the vector dotted with itself, right? Similarly, we define the norm here as the square root of the strain energy. You have a question?
Yeah, what functions would you use if you had different type of problems?
Yeah, that is a great question, actually. So what functions you use? And so far, we are still working in an infinite dimensional space, right? That basically means that the functions U that we are interested in can be written as the sum of an infinite series of functions, basis functions times the degrees of freedom. But the moment we go to a Galerkin approximation, and this is what we're going to do next, and we say, well, I don't want to live in an infinite dimensional space because to start with, I cannot use an infinite dimensional space. I want to be able to solve this type of problem in a computer, right? That has finite memory. So I'm going to relax that requirement. I'm not interested in finding the exact solution. What I'm interested in is in finding an approximate solution, right? That has an error level that I can live with. So the moment that you accept that, so you relax that strict requirement on finding the exact solution, then you say, well, what are the types of functions that we can be using? And there are tons of different families of functions, but in finite element analysis, we normally use polynomials. Yeah, so we look at polynomial spaces, and in particular, we are interested in something that is called Sobolev spaces, which are functions that are square integrable, because remember that we're not interested in something that has infinite strain energy. So these are functions that are square integrable, and that they have derivatives that are also square integrable. So the Sobolev spaces, and you probably, if you ever read a paper on finite elements, you see that there are these H spaces, H1 for instance. H1 denotes the Sobolev space that is comprised of functions that are square integrable, and that the first derivative of those functions are square integrable. So normally we work with these spaces in finite element analysis, right? And polynomials are part of this it's a subspace of this H1 type of space, okay? But yeah, this is getting a little bit mathematical. Remember that we are going to look at some mathematics in this course, but not so much that you guys go crazy. No, this is a mathematical course. I never want to see finite elements again, okay? But you're gonna have some tools, all right? Okay, so I think now we are ready to proceed, because now that we have everything in place to write the variational form, right, we are going to do something nice. We're going to work on this particular term, because who can tell me what is the derivative order on u in that term? Second order. And what is the derivative order on the test function? 0th. And what we do, right, is we try to balance these things, right? Why? Well, because the moment we balance this and we talk about finite element spaces, right, then we can adopt certain functions that you would normally not use, right? So the moment I have my weaker variational form, if I balance derivatives on this term, then I can, for instance, choose linear polynomials as an approximation to the problem that otherwise I could not use because it requires a second derivative. You understand that? Okay, so but before we talk about this, let's get there. So we're going to do integration by parts on that term, and if you remember the integration by parts from your previous courses, well, you know that the u dv is equal to uv minus v du, right? So if we look at that particular term, then I want to balance the derivative on du dx. So that particular term is going to be written as essentially we're going to be evaluating EA, that term at 0 and L minus the integral, and this is where the balanced derivatives come into play. So we have EA dw dx du dx. Yeah? So then what we just did, we apply integration by parts to this term, and then we can bring all this stuff back to this equation, right? And then let's see how it looks like. So then what I'm going to do is I'm basically going to move, when I bring this whole thing back, this has a negative side, so I'm going to move it to the other side, of the equation. So then this whole thing is going to look like so this other term that was negative, you see the SU is of course going to go to the other side as well. And that is going to be equal, and what is left on the left is of course going to be this term here, right? And there is this term over here that does not depend on u. And you will see why I'm basically sending everything that depends on u to one side of the equation, and everything that doesn't depend on u to the other side of the equation. Yeah. Oops. Yeah. So what I'm going to do now, this is the equation, and I balance derivatives, as you can see. What I'm going to do is I'm going to call this term here B of u and w, and this term here I'm going to call it L of w. And so my weak form, yeah, so the weak form is going to read find u in that energy space, yeah, such that the bilinear form is equal to the linear form for all functions w in that energy space. Yeah. Now, of course, I forgot here to put this guy, so I'm going to copy and I'm going to paste it here, although it's too big, so never mind. Yeah, so this is the way our weak formulation reads. So find u that belongs to that energy space such that the bilinear form equals the linear form. And why is it called the bilinear form? Well, because if you see my bilinear form, every single term is a function of the trial solution u and the test function w. Right? So you have this term, it depends on u and w, and you have this term that depends on u and w. And everything that you have on the right depends solely on w, right? You have this term, there is no u here, and here there is a u.
Yeah, but that's the boundary condition.
Yeah, that's a boundary condition. So that is something we know. Yeah, so actually we're going to replace this term by our boundary condition. Now, that is not the only thing that we're going to do, because, for instance, what happens if I don't have an axial force boundary condition, but I prescribe the displacement? So then this term basically involves what? If I prescribe, let's say, the value of the displacement at the left end, right? This term here is still an axial force at that end. What is that axial force? If I prescribe the displacement. How do we call that particular force? If you prescribe the displacement, the force is the reaction. Uri, come on, man. You're on fire. It's a reaction force, right? Now, in many cases, we are actually not interested in what is the value of the reaction. So we're going to apply a trick. We're going to smartly choose our functions so that this w here is going to be 0 at that location. And that is actually what we normally do in all problems where we set up the finite element method, right? Because I'm not interested in the reaction, I'm prescribing the displacement. I don't really want to have the reaction messing up in the formulation. I basically choose the test function so that they vanish at that location. That's how we do it, right? By the way, you can keep the reaction in the formulation and you can actually also solve for it, right? But that is not straightforward. We don't do it that way, okay? So let's talk a little bit about the properties of this bilinear operator. Well, these are also all listed in the, by the way, in the all the information that we're going through now is also in the book chapter that you are reading the Nota Bene right now. So in addition to following the videos and the lectures, please also follow the book, because there is additional material that you may find also very interesting. Okay. Okay, so what are the properties of this bilinear operator? Well, for u, I'm going to take some functions u, v, w that belongs to some space v, and for some c that is just a scalar. Then the properties are, well, the bilinear operator of u comma u is always greater than or equal to 0. Actually, the time where it is equal to 0, right, is when, if you think about it, you either have the trivial solution, right? You have the trivial solution, u is equal to 0, that is going to give you the bilinear form equal to 0, right? And the other is when? Yeah?
The length is 0.
The length is 0? No. Well, of course, it doesn't make sense for us to solve a problem in something that doesn't have any measure, right? So assuming that we have a bar, then when do you think we have basically the bilinear form equal to 0? Keep in mind that the bilinear form has a relationship with strain energy. When the strain energy is going to be equal to 0? Yeah, there you go. You have a rigid body motion, right? In that case, also your bilinear form is also going to be 0, right? Okay, so that is one of the properties. Then of course you have a symmetry property. So b of u w is equal to b of wu, right? Then you have, and that is actually very, very easy to check. So if you look at this equation and then you just swap u and w, you immediately see that it's actually the same expression. Okay. Then you have another property, the distributive property. So b of u plus v comma w is actually equal to b of u comma w plus b of v comma w. And of course, this is a little bit more difficult to see, but you can actually try it out. For instance, if you try it out in again using this bilinear form, you will see that actually holds. And then finally, b of c times u comma w is equal to c times b of u comma w, which is also actually quite straightforward to realize. Yeah. Okay. So as I said a minute ago, if you remember, the way we induce a norm in the energy norm, right? The way we induce this norm to measure what is the behavior of a function, right? Remember that now we are not working anymore in Euclidean spaces. These are function spaces. The behavior is similar or analogous in many different ways, but they are still different. So these are different animals. Okay. Now remember that you have here u. So that's our strain energy, which can be computed like this, right? And now, if you compare all of these expression on the strain energy, and you also see what this looks like, right? Basically, if I take the bilinear form and instead of having b of u comma w, I have something like b of v comma v, then I'm going to get something that looks very similar to this. Actually, almost identical. So then there is a relationship between this norm and the bilinear form. And that is what I want to write now. Yeah? So in other words, if you compare the bilinear form with the strain energy, what you get is basically u of u is equal to 1/2 of b of u comma u. So they are almost identical except for that half. And well, by extension, if you remember the way we define the norm in the energy norm, right? I can actually write this as the square root of 1/2 of b u comma u. And this is actually the way we compute the error in the energy norm in the computer. So once you solve a finite element problem in the computer, you basically get the strain energy, right? And you immediately have that error in the energy norm by computing the strain energy, right? Because of all these relationships between the norm, the bilinear form, and the strain energy. Okay? Okay, and there is one little thing that we have to consider one more time, and it's what happens when I have a non-homogeneous essential boundary condition. So who knows what that is? A non-homogeneous essential boundary condition. No one? Okay, let's take a look at the bar. If I prescribe the displacement at one end, I can prescribe a 0 value, right? In that case, that point is not going to move anywhere, right? But I can also prescribe a finite value. So in the former case, I'm prescribing a homogeneous essential boundary condition. In the latter, I'm prescribing a non-homogeneous boundary condition. And actually, it may be like silly to describe one or the other, but mathematically it's actually very, very important. And the reason for that is that we're actually working with spaces, right? And the moment I choose a function that satisfies a non-homogeneous essential boundary condition, I am no longer talking about a space anymore, because a space, a function space, has to have this notion of a closure of a space, right? What that basically means, and I'm going crazy in mathematics, right? But bear with me, right? This is not mandatory to approve the course, right? But bear with me. So what closure of a space means is that if I take two functions from the same space and I add them up, the resulting function has to belong to that same space, right? Now, if I take a function, let's say I prescribe the displacement at the left end, and I say, well, the displacement is going to be equal to 1 what? Doesn't matter, 1 centimeter, for instance, right? So I take one function of that. That function is going to have a value of 1 at that location, and I add it to another function. Then what is going to be the displacement at that location? If I add these two functions, what is the value of the displacement at that location?
1 plus the other function.
Yeah, which is? Say one is 1 and the other one is also 1 because both belong. Yeah, it's equal to 2. Now you see that the resulting function does not belong to that space. Okay? So that is not called a space anymore. It's called a set of functions. Because a space, the word space, has to have some properties. Otherwise, it's not formally known as a space. Okay? Now, let's go back from the crazy mathematics, right? So how do we get around mathematically this idea? Well, when you have non-homogeneous essential boundary conditions, yeah, what we do is basically create a function that is the sum of two functions. One that belongs to the set that prescribes the actual value of the boundary condition or the displacement that we want to prescribe, and the other one that does belong to the space. So that is how we go around this, right? So we can say, given a function u that is going to be the sum of two functions v plus u tilde, and this u tilde is my function that I know satisfy the boundary condition that I want. So basically that you can write where u tilde at gamma u. Remember that gamma u is that part of the boundary where you are prescribing Dirichlet or essential boundary conditions. That is equal to my prescribed value of the displacement, right? Then our basically weak form of the problem is find v that belongs to some space. Now I'm talking about space, and I'm going to explain what this v naught means in a minute, such that, well, b of u comma w is equal to L of w. So I have not changed anything so far for all w's in that space v naught, right? But now I'm going to see what is that v, and I'm going to write it like this. So it's basically this u is v plus u tilde. So when I do that, I basically get this equation. I'm going to move this to the right. Yeah? And well, what is that v naught? I'm going to define it as the space. It's a set, but it's also going to be the space of functions b that belong to this energy space, but also that when I evaluate that function in the part of the boundary that has prescribed displacement, that is actually going to be equal to 0. So that is the way I define my v naught space. I will explain in a second everything again, and keep in mind that there are some concepts that are quite abstract in this course, so it's going to take you 2 times, 3 times to understand these concepts, right? But what is the thing? What is happening here? If you remember, can I continue? Everybody's done writing? Yeah? Okay. So if you remember, we came to what is actually our weak form before, and we said, well, the bilinear form is equal to the linear form. That's what we did. And so far, remember, we're still in an infinite dimensional space, so we cannot solve the problem with finite elements yet. Not yet, right? But let's imagine that we're in an infinite dimensional space. And now, the moment I go to a computer, this term, of course, is going to bring me my stiffness matrix, right? And this term on the right-hand side is going to be my force vector. And then you're going to be solving a system of linear equations, Ku equals F, okay? So the bilinear form is going to lead to my stiffness matrix. My linear form is going to lead to the force vector, right? So all we did, if say we have non-homogeneous essential boundary conditions, is I just decided to write the solution. So my trial solution U is going to be just the addition of 2 functions, right? One function V that belongs to the same space of functions as the test function. So if you see, my V belongs to V naught, and all test functions, all weight functions belong also to that V naught. So then this is great because I have symmetry. So I'm choosing both this V function and the weight function from the same space of functions. This is what I want. Otherwise, then we have some issues there. We have a different type of Galerkin approximation later on, right? So choosing both the trial solution and the weight functions from the same space lead to what is called the Galerkin approximation, and that gives you lots of nice properties, right? The matrix, the stiffness matrix that you get is symmetric, is beautiful. You can solve it by something called Cholesky factorization that uses less operations, and so on. There are some nice properties, right? So what did we do to handle non-homogeneous boundary conditions? We just simply write the trial solution as the sum of 2 functions, one that I take from that space that I'm interested in, plus another function that satisfies the non-homogeneous boundary condition. And when I do that, you see that this guy here, the contribution of that known value of the displacement goes to the right hand side, which is that it's going to be part of what?
Bilinear.
This term here becomes part of later when we do finite elements. It's going to modify the force, which makes a lot of sense, right? Because if you happen to know something about the problem, right, it's not an unknown anymore, but I know that the displacement here is going to be 2, right? Of course, you expect that you're going to use that information, right, somehow. Well, in this case, that is going to be modifying the right-hand side. Okay? And by the way, choosing functions from this space so that V also basically is 0 at the value, is 0 at the location of where you are prescribing the displacement, has the added benefit that you are not dealing with the reaction anymore. Remember that we were here and we say, well, what happens in this term when we have some prescribed value? Well, this is a reaction, but because W is chosen from that V naught space, this term basically goes away from the formulation. Okay? So I think I lost a few of you. But again, it's going to take some time for these little abstract concepts to settle in your mind. So don't feel scared. It's going to work out. Now, does anybody have a question about this? Yeah.
Could you maybe explain again why the like the V on the right hand side contributes to the force and not to, for example, the stiffness matrix?
Because it's known, right? So if you see our bilinear form, right, the U is the unknown part.
Yeah.
So this U, well, so this term here is not known.
Yeah.
So we don't know the solution. Actually, we need to solve for the solution. Now, everything that you have here on the right is known, right?
Yeah.
And one may ask, well, do we know W? Actually, you are setting that equation so that it is valid for all W's in that space, right? How crazy that is. Well, later you will see when we get into the Galerkin approximation that this expression is going to be greatly simplified, because by saying that it has to be valid for all W's in that space is going to translate into having something in brackets be 0, and that is our system of linear equations. Okay?
Okay.
So again, to answer the question, everything that we know about the problem goes to the force vector, right? Everything that has the unknown goes to the left side of the equation, and therefore it's going to be part of the solution, right? So your U, your KU equals F. U is the displacement vector that we're interested in, that we're going to solve for. Okay? Other questions? And that is the reason, again, why this term shows up here, because there is no U. It's U tilde, but we know U tilde. U tilde is the value that you want to impose.
Okay.
Okay?
Yeah.
Yeah?
Do we have like a short break?
Yes, now we take a break, and then we have, now this is the moment of the break. I'm taking a break because after this we basically get into the Galerkin approximation, and we're going to finish today with the Galerkin approximation.
How long is the break?
Let's take 10 minutes?
Yeah.
Yeah?